Okay, good morning, students. We start in 1 minute. Okay, let's see if some more people join. So is my screen visible? Someone? Is my screen visible?
Yes, sir.
Yes, sir.
Okay, good. Okay, students, let's start. So I'll continue from where we stopped yesterday. Now we are talking about different properties of nanomaterials. Okay, so their electronic properties, magnetic properties, optical properties. Now, if you remember, I had shown this type of a plot. Actually, I had drawn it once for you, where I was talking about the change in band gap with the size of the nanoparticles. And this plot that you see here is specifically of a material called indium phosphide. Okay, so the nanoparticles are indium phosphide, and this is a realistic measurement. Okay, so all those points that you see there, these are sizes or diameters measuring using two different techniques. Okay, one technique is called X-ray diffraction, that is XRD. All right, all those square dots, that's XRD, and the other one is from a transmission electron microscope image. All right, so people have plotted and they see this trend coming in. Okay, so this trend, so you see when diameter is less, okay, that means as it goes smaller and smaller, the band gap goes on increasing. Okay, so that is a a typical you'll say a property of nanomaterials, that you can actually tailor a band gap. That means depending upon what type of band gap you need for a particular application. Suppose you are making something that calls for a band gap of maybe 2 point something, say 2.2, of course. Okay, then you can actually think of, if you're using indium phosphide, then you can think of this size, right? This is 2.2 band gap, so it will be roughly about 17 or 16 nanometers. Okay, so these type of plots can give you a lot of information, and you can actually plot them yourself, so using various techniques. But remember this, that smaller is the size, wider will be the band gap, and wider the band gap, more energy is needed for conductivity. More energy is needed to transfer an electron from the valence band to the conduction band, right? All right, moving on to the next slide. What happened? Okay, continuing with the electronic properties. Now, whatever we're talking about, the band gap, that is also an electronic property. Okay, that affects the absorption, of course. The main means the optical property also is dependent on the electronic property. So these are some observations that I've put down here. The electronic structure of nanomaterials is different from its bulk material that we already discussed. So electronic property changes because of the change in the band gap, right? And if you remember, we were discussing yesterday, we said that as the material gets smaller and smaller, the lattice constants also change. That means the spacing between the atoms also changes. That means it becomes smaller. Now, if the spacing between the atoms becomes smaller, then the interatomic interactions, the energy that holds the atoms together will be even stronger, right? So you have two charged particles and their interactions, if they are nearer, will be more as compared to if they increase the distance. And that's why atoms in a nanomaterial are very, very strongly bonded. Okay. The density of the energy states in the conduction band changes. Now, what do we mean by this density of states? Okay. Again, if you remember, I was talking about this yesterday when I said that a bulk material, the allowed energy levels in the conduction or the valence band is continuous. That means any energy level, the electrons can transitorily shift there. Okay, can go there and stay for some time. But gradually, as we go smaller and smaller in size, these get discretized. That means not all the energy levels will allow the quasi, stay of a electron. Okay, that means quasi-stable energy states. Not all the energy levels are allowed. Okay, so only discrete. That means specific energy levels will allow that. Now, what do we mean by density of states? Okay, so basically mean that how many, and at a particular energy level, how many of these allowed states are there. Okay, so say that we were just now talking about say 2.2 electron volts. Okay, so at 2.2 electron volts, how many levels, that means say very near, say talk about say 2.2 2.21 2.22 2.19 2.18, suppose these four states allow your electrons to be there, okay, but the others won't. So we will say that 4 in this energy value will have, 4 is the density of state there. Okay, so it's basically per unit volume. Okay, the per unit volume for every specific energy. Okay, so you can say per unit volume per energy. So the density of state, that means the number of available states, plays a major, you can say very crucial role in the electronic property of the material. So when the energy spacing between the two energy levels is more than a value called kBt, the energy gap is created. That means the energy gap, okay, is possible when the energy spacing is a multiple of kBt. That means Kb is the Boltzmann's constant, T is a temperature in Kelvin. Okay, so this is the amount of energy gap that starts the what we call as the semiconducting property. Now, nanoclusters of different sizes will have different electronic structures and different energy level separations. Okay, even with the same material, if we decrease the size, vary the size, then the energy level spacings will also vary. The density of states will also vary. The ionization potential at nano sizes are higher than that for the bulk materials. All right. So the ionization potential basically refers to the amount of energy that is needed to free an electron from the control of the central nucleus. All right. That means basically the amount of energy needed to break free. We can also call that as a work function. So the ionization potential. So you know what is ion, right? I already told you what is ion. When an electron is removed, one or more electrons are removed, then an atom becomes an ion. And that's why to remove the electron, whatever energy is needed is called the ionization energy, right? So since the band gap increases when the particle size goes smaller and smaller and smaller, obviously you will need more energy to separate out the electrons, right? And that's why the ionization potential goes higher at the nanoscale. So here, if you see this figure, it shows basically just like a schematic diagram showing the energy levels. Okay, when we are talking about density of states, so these are the energy levels. Okay, so for a bulk material, this is a bulk material band. So you see here, this is continuous. There is no break in the conduction band or the valence band. That means the electrons can be anywhere. They are allowed. Okay. Now moving over to a nanoparticle, you see here they become discrete. That means, so these are also discretized. So suppose an electron is here, it can jump up to this one. All right, because this is allowed. But if it gets more energy and it goes further up, say in between these, it cannot stay there, but it will lose some amount of energy. All right, it will lose some amount of energy and fall back to this level. All right, so these are only the allowed levels. Okay, and this thickness that you see here, this is thinner than this one, right? This talks about the density of states. That means at this energy level there are less number of available states. At this energy level there's more. At this energy level it's even bigger. It's a huge number of energy levels available. So that's how is the depiction in this figure. That's how it explains. Okay, it's a very generic figure. And if you talk about an atom or a molecule, okay, then the state of the energy of the electrons, we use two other terms. We don't say valence band and conduction band at the atomic or molecular level. Okay, so we say HOMO and LUMO. So HOMO basically means highest occupied molecular orbital, or it's given here highest occupied molecular orbital, and LUMO is the lowest unoccupied molecular orbital. Okay, it's very similar to what we are talking here in the for other materials, mostly semiconductors. Okay, but at the atomic level we use these terms. Now looking at these nanomaterials here, okay, we already mentioned about 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional nanomaterials, right? So 0-dimensional basically we refer to the quantum dots or the very small nanoparticles. These are maybe nanowires or nanorod like structures in the 1-dimensional, and in the 2-dimensional we talk about thin films where the dimensions on these two sides is large, goes into the macro scale maybe, but this dimension here, the thickness is in a nanoscale. That means less than 100 nanometers. And this is of course the 3D, but even in nano size, if one of these dimension is, sort of nano, then we call it the three-dimensional or hierarchical structure. But this figure here is talking about bulk material as such, right? Now, let's try to understand how the variation in the density of states take place. Now, if it is a bulk material, so this is the energy plot. Okay, that means energy increases this way. Okay, so energy is increasing this way, and if you look at the density of states, okay, as the energy is increasing, the density of states is gradually increasing. All right, and after a certain energy level, this saturates out. Okay, so this is gradually increasing the density of states. Okay, that means higher is the energy, more will be the available states. Okay, let me try to draw this for you. I have another slide. Okay, here. So you see, I've pulled in that same figure here. So this is for a bulk material. For a thin film, the variation with increasing energy, that means the density of states, it happens like this, that all of a sudden there's an abrupt increase in the number of available states. Okay, and then till a certain amount of energy, it remains constant. There's no more increase in the density of states. Then after some energy, as you go on increasing, again abruptly jumps up. There's a lot more abruptly, and then again it saturates out. Okay, again it saturates and it goes in like that, like a staircase. Okay, for a one-dimensional nanomaterial, Okay, again it happens very similar to this abrupt increase. Here also abrupt increase, but then it gradually falls down. That means abrupt increase in the number of energy levels. Then as the energy increases, the number of energy level goes down to 0, and then again abruptly it jumps up. Okay, again goes down to 0, again abruptly jumps up, and this jump is gradually increasing with more energy. And for a quantum dot or a zero-dimensional nanomaterial, these are abrupts. Okay, that means all of a sudden at particular energy level you'll have many allowed states, then there's nothing, again many allowed states at a particular energy level, and then again nothing, and then it goes on that way. Okay, I hope you understand. Or let me see. Okay, let me try to see if I can. Don't see it. I don't know why. Just a minute. I can't see this. Yeah, that's the pen. Let me use a different color today. All right. All right. Say let us talk about this one. So as I said, so the let me say this is the valence band. This is sorry conduction band. This is the valence band. Suppose. All right. Now we're talking about the density of states. So initially, you know, the density of states will be 0. That means if this energy gap is very small, okay, the density of states will be 0, and gradually as we increase in energy, okay, so we're talking about here now, so gradually we are increasing in energy, all right, and the density of states, if I draw lines like this, okay, these are very dense here, all right, and then this density will go on increasing. That means as we grow further, this will go on increasing. It means the gap between these energy levels will be lesser and lesser. Okay, so let me zoom and draw. I think what I was trying to say is that if this is the conduction band, it goes something like this. Maybe suppose this is how it is, and as you are going more and more in energy, the gap between the energy levels is getting smaller and smaller. Okay, and it goes that way, right? So the density will be more as we're going, and then finally, yeah, all this drawing is done. Finally, you see when you come to this stage, then it's almost saturate out. That means after that, no matter how much increase in energy goes, this separation between the energy levels is almost constant. Okay, hope you understand this. Now talking about this one, the two-dimensional material. So what happens here is, if I can draw the conduction band, and now this goes same for both, okay, for this the valence band. So in this case, it's an abrupt increase, right? So it's an abrupt increase, okay? These are the energy levels. Then, of course, this will continue. That means this will continue. Once it reaches this abrupt value, this will continue. Difficult to draw with the stylus. And then it goes, the next energy level here, it again abruptly goes up. Abruptly goes up means what? The number of energy levels or the density of state goes up means what? The spacing between the energy levels will decrease now. It will be very, very narrow, right? Very, very narrow, and it will go on like this, and it will maintain it again till it goes to the next level where it becomes even more denser. It's difficult to draw, but I hope you understand. Okay. The same thing if I take this case of the one-dimensional material, here also this is abrupt. Okay, that means the increase in energy level, it goes to a certain energy level abruptly. All right, suppose we are going here, and then gradually it will fall back. That means gradually this will become wider, all right, till it comes down, and then abruptly again it goes higher. That means again it will become very narrow, very narrow, like this, all right, and then again it will slowly broaden out and fall back this, and again it will be dense, right? You understand? Again it will be difficult to draw with this. Anyway, again it will be very dense. Okay, so that is what is this one. And here, of course, this is very discrete in the quantum dot or the zero dimensional material. If I draw it here, it is very discrete. That means at a particular energy level, suppose I'm drawing diagonal, this is there, then again these are there, and again, and you see with the increasing energy, these spacings will go on decreasing. That means this inter-level spacing will go on decreasing because the density is increasing. So if the density has to increase, this means the spacing between them has to decrease. Okay, all right, fine, hopefully you understand. So this is for zero dimensional material. All right, so the here we are again showing that figure of the discrete levels. Okay, so this is for an atom or a molecule. So the atom is very singular, only one state, homo lumo states come in. Okay, so this is lumo, this is homo, because normally this one is the highest one with the electrons. Okay, the top of the molecular orbitals, and this is the bottom of the molecular orbitals in the other stage. Okay, so this one is least occupied and this is one is highest occupied. Okay, so now we go to a cluster. Cluster means a few molecules or atoms together. That is the starting of a nanoparticle. Okay, we start with a cluster and these clusters add up to become a nanoparticle like this, and this is how it goes on. You see the variations in the position of the energy levels. Okay, and when we go to a bulk material, this is a semiconductor material. There will be some energy difference between the valence and conduction band, but in a metal, like this is a semiconductor, say, and this is a metal. In a metal, they will overlap. Okay, and that's why we have so many free electrons in a metal. Okay. Now let's talk about the surface, because surface is something that is crucial. Okay, as for nanomaterials, I already told you that the surface to volume ratio is extremely high. Right? That's why, and the surface is always different from the bulk. The surface is always different from the interior part. So the way that the surface atoms behave is different than the way the atoms inside the material will behave. Mostly because the surface atoms are loosely bonded because they have less number of neighbors, immediate neighbors, right? So the surface atoms will have less number of atoms surrounding them as compared to the atoms inside. The atoms inside the material will have more atoms surrounding them, and that's why they have more restrictions. Okay? They cannot quickly react because the bonds are already not available. They are already used up in bonding with all these atoms. But those at the surface, since they are not surrounded on all sides, there are certain bonds which are free. Right? So they can easily bond, they can easily react. Okay, and that's why we say the surface reactivity is extremely high. So as the surface atoms can easily react and nanomaterials have more surface atoms, so obviously nanomaterials will be more reactive as compared to a bulk material of the same type, right? Now, talking about optical properties of semiconductors. So we already talked a little bit about metals, where we say that the color that we see of metallic nanoparticles is based on what we call as surface plasmon resonance. We discussed this yesterday, where we say that light falling on a nanomaterial or any metal, okay, they interact or have an interference with the natural frequency of the electrons on the surface, and based on the resonance that happens, we see the color. Okay, whatever wavelength the resonance happens, we see the color at that particular wavelength because the signal is radiated out. So for semiconductors such as zinc oxide, cadmium sulfide, okay, these are different semiconductors. Silicon, you know, is a semiconductor which is used by the electronic IC industry, right? The band gap changes with size. Okay, when the band gap lies in the visible spectrum, changing band gap with size means a change in color. right? That means if the band gap, whatever energy is there, falls within the visible spectrum, that means the energy of the photons that we can see, all right, violet to red, that VGR, right? So if the band gap is within that, then obviously visible light photons energy will be absorbed for this transition from valence to conduction, and that will affect the color because we can see. If it is in the ultraviolet or in the infrared, we will not see, right? So it has to be in the visible, meaning the band gap will be comparable to the visible region. Since electronic transitions from the valence to the conduction band span a fairly large range of energies, semiconductor act as a sort of a long pass filter, right? So that means the energy band that can actually pass through, right? It's huge. It's very big. That's why we normally call them as wide band gap semiconductors. Okay. So what is the color we see? Like a flower is red. Suppose you see a red flower, a red rose maybe. So why is the red rose? Why is it not black or green or blue? Because the rose flower is absorbing all other wavelengths of visible light except red, right? So red, it is not absorbing, it is reflecting it back. So anything that is not absorbed by a material and reflected back, that is what we see. All right. Now it is not very discrete. You cannot say that no, this material absorbs blue, all right, or absorbs green, because this is a continuous band. All right. So we say that violet is starts from 400 nanometers, but for exactly 400 nanometer is not only violet. Violet will slowly fade into 401, 402, 400, maybe up to 400 something, say 405 or 410, and gradually violet will shift to indigo, right? And again it will continue for certain wavelengths, and then again at a small band, and again it will shift to blue, then green, then yellow, and it goes on that way, right? And that's why we say, or when we observe what wavelength this particular material absorbs, because if you see a red rose can have various shades of red, right? Some are very deep red, some are light red, some are maybe slightly orangey, right? So all these happens because of different wavelengths being absorbed by the material and some wavelengths being reflected back. So the combined effect of the reflected wavelength is what we see. All right. Now these are some typical band gaps of these semiconductors, some semiconductor examples we're talking about. So zinc oxide is a typical semiconductor. And if you look at zinc oxide, okay, it is white in color. Okay, it's a powder, it's a white powder, or powder in the sense that if you have it in powder form, you can have it in thin film form also, whatever, but it is white in color. And the band gap is more than 3 electron volts, right? So it basically moves beyond violet, all right? It moves beyond violet. So anything beyond violet is ultraviolet, right? So basically then zinc oxide will absorb ultraviolet, will reflect back everything. That means all the white light, violet to red, it is reflecting back everything, and that's why you are seeing the combined effect, which is white, right? Because that is white light. White light is composed of all these colors. The moment they are together, all of these colors, it appears white, right? So zinc oxide will appear white. Now the band gap for cadmium sulfide is smaller. It lies in this range, which actually conforms with the wavelength for yellow, right? Actually, it's from yellow to orange in that range. So you will start seeing cadmium sulfide nanoparticles in the yellowish range of the color. Similarly, gallium phosphide, the band gap is between 2.3 to 2.5, which conforms to orange. All right, so you'll see gallium phosphide nanoparticles as orange in color. Okay, and go on that way. So mercuric sulfide is even less, 1.8 to 2.3, and you see it red. All right, cadmium selenide goes very close to 1.8. Okay, and that actually allows complete absorption of the white light. All the bands absorb, so whatever you score, there's no light actually reflected back, and that's why you see black. All right. Silicon is 1.1 or 1.12 is the band gap of silicon. Okay. So silicon extremely small band gap, extremely high energy. Okay. So thin slices of silicon will appear transparent to you. So continuing with the discussion on semiconductors, the optical properties of semiconductors, metals is a different issue altogether. The metals behave differently because of overlapping of the valence and conduction band, but in semiconductors there is a spacing between the valence and conduction bands, right? Just a second. So give me 1 second. And it's more class চলি আছে callback কৰো okay so just what I was saying, that if a material absorbs, so we get the complementary colors. That means the major color that is absorbed, what you see will be a complementary color. Say, suppose the material absorbs violet light, you will see a complementary yellow light. All right. A material absorbs green light, you will see it more in a reddish way. Okay, reddish. That means we see that gold nanoparticles are red in color. That means at that size range, it is actually absorbing maximum of the green light. Okay, because these are the dominant colors. Okay, a material absorbs violet, blue, and green, so it's a wider band gap, is absorbing more colors, and we'll see between orange and red. There's a variation of the red. Okay, more towards orange. Similarly, material absorbs red, orange, and yellow, then we'll see it blue. Okay, that means gold nanoparticles or silver nanoparticles mostly come also blue. So depending on the size and the shape, okay, the absorption it varies and the color varies. So no magic in it, but I will sometimes show you. It's in our lab also because we are doing a lot of work with silver. One of my PhD scholars is working with silver, and he has beautiful colors to show of silver nanoparticles. Beautiful blue color to red color to yellow color to pink color. You won't believe it. Any color you can name it just by tailoring the size and the shape. Okay. Now, if you talk about the typical energy, all right, this is a formula for calculating energy of a wave. So it's hc by lambda. Okay, so h is Planck's constant, c is the velocity of light in vacuum, and lambda is the wavelength of light you are talking about. Okay, the photons. So if you plug this value in here, the Planck's constant is given here below, and you know c is 3 into 10 to the power 8 meter, right, per second. So if you plug this value in, you come to something like this: 1240 divided by lambda is a variable now, lambda in nanometers. Okay, you can try this. If you plug this value, you will find something like this: 1240 by lambda, and that's a generic formula we use. That what is the energy of a wave with or a photon with wavelength lambda? You will say it is 1240 by lambda. Okay, so you can simply calculate that out. Like say ultraviolet. Normally, you know, below 400 we call it ultraviolet because 400 is violet. So below 400, so if we talk about this range, 100 to 400 nanometers, then the energy will be from 12.4 electron volts to about 3.10 electron volts. Okay, so for violet, which is just in this range, 400 to 425, this will be in this range, 3.10 to 2.92 electron volts. Okay, so gradually as the wavelength increases, the energy will decrease, obviously, because wavelength is the below in this one, no? In the ratio plot is below, so inversely proportional to lambda, right? So these are the different calculations for the different colors, the band, energy band, right? And infrared, okay. Now when we say use this term near, it means it is very close to red, just after red. Similarly, we say near UV, which is just close to UV, far UV, okay. Similarly, we say near IR and far IR. Right? So 700 is red, so beyond 700, we call it as near IR, okay? And this is the energy band, I mean the variation in the energy in electron volts. Okay. Now these numbers might be interesting for your exams also, okay? But please don't you don't have to mug up these values. You don't have to memorize these values because formula is all that you want. If you have this formula, it's very easy to calculate the energy from the wavelength. Okay. So again, this is a repetition of what I said before. Bulk gold is golden in color, but nano-sized gold is mostly red, right? But it can go even to gray and black also, depending about the size. But those particles are not very stable. The most stable particles are the red particles. Okay. So the particles are so small that electrons are not free to move about as in bulk gold, right? I told you, no, because in nanoparticles, we are constraining the movement of the electrons in almost all directions, all the dimensions, because it's a quantum dot, it's a small one, it's a zero-dimensional material. But in zero-dimensional material, we are restricting the movement of the electrons in 3 dimensions, okay? And but in bulk gold, it is moving around free to, it's like it's a metal, so it will just move around, okay? So color of nettling nanostructures is mostly due to surface plasmons. Okay, so these are 12 nanometer size particles, and you see they are red in color. Now, I don't know if you know, but most of the sunscreen lotions use sunscreen during summer, right? When they're moving out into the sun, they use zinc oxide. Now, the reason why they use zinc oxide, because the role of the sunscreen lotion is to simply block the ultraviolet light, because the ultraviolet light has an effect on your skin. Right. So at one time I was working a lot with ultraviolet light because I was working with zinc oxide and zinc sulfide. These are absorbed in the ultraviolet region. So I was working under ultraviolet light illumination. If I happen to put in, or it happened with me a number of times, I quickly put my hand in, without any gloves or covering, and I can feel, even smell my, the hair on my hand burning. Okay, I can smell it if I can get near my nostrils, right? So they have a bad effect, and that's why your skin darkens up, all right, if you move around in the sun too much because of UV exposure, and you might have a lot of skin problems also. I had a problem for ages, I can say. I suffered for about 10-15 years because I used to drive a motorbike, and my motorbike had these rear view mirrors, and during summertime they reflect, and light is concentrated on my hands, and I used to have white patterns, small white patches all over my hands, and they were very itchy, very itchy, I tell you. I've been meeting so many doctors, the problem could not be solved, especially when I was in Guwahati. And then finally, when I was in Thailand, I met a doctor, a lady doctor, with her team from a government hospital. And she actually explained to me a lot of stuff about how UV can actually affect your skin. And she gave me a concoction. Actually, she gave me 4 or 5 different medicines put together, mix it, and I used it. And believe me, that was in 2006 or 7. Until now, those things have never reappeared. So I don't know what was there, but anyway, that's just off the track. But see, the thing is, zinc oxide as a material will always absorb UV light. Okay, be it in a bulk form or be it in a nano form. But if you look at the bulk form, like I told you, it will be white, right? It will be white because at that wavelength, it is absorbing, it is absorbing in the UV and reflecting back all the infrared and IR, all right? And all the, all the visible light and IR. So if the visible light, all the visible light is reflected back, you will see it as white, all right? So that's why if you look at this lady here using sunscreen lotion, this is bulk zinc oxide being added, and that's why the color is white, right? But you know what happens is, this is because the bulk, they absorb UV light and scatter, right? Scatter the visible light. We use the term scatter, which is sort of like reflection, but reflection follows the laws of reflection. Scattering does not follow the laws of reflection. You all know the sky is blue. You know why? I'm sure you should know. We have studied this in school. It is because of scattering of visible light by dust particles. All right. That means if you go up, take a plane and go up, you will never see the sky blue. You're seeing it from the earth because the light that is scattered, okay, scattered means when light grazes over a surface, very thin, very small surfaces, then they break down into their individual components. All right, that means visible light will become all the colors, and that's why we see the rainbow and everything. They break up into all the colors, and break up in the sense that the amount of deviation, amount of change in direction depends upon the wavelength. All right, that means blue light will go in a particular direction, red light will go in a particular, like in a prism. You see that, no? It is separate out, and we see the sky blue because the blue light directly comes towards the earth. Right, and that's what we see. That's a major component, and we see the sky as blue. So it's all about scattering. Okay. Now, what happens in the nano size? If you use a nano size sunscreen, sunscreen lotion that says we have nano zinc oxide, you will find it is transparent. It is not white. Okay, because at the nano size, it will obviously block the UV light, but it's so small, compared to the wavelength of the light. That means, you see, we are talking about wavelengths in the range of 400 to 700 nanometers. That's the visible range, right? But the particles are just 5 to 10 nanometers. They're extremely small, as compared to the wavelength, right? So small wavelengths, particles, so they hardly can scatter the light, right? That they don't scatter it. Okay, this is a TEM image of some zinc oxide nanoparticles. Okay, not very nicely made. As you can see, there's a wide variation in the sizes. These are the ones that are commercially available. You can buy off the shelf, but if you make yourself very consistently, you can make beautiful particles of almost the same size. I'll show you some images that I made. I have images like this of particles I bought also and particles I made also, and you see why difference. All right, so these type of particles that you buy off the shelf are not really good for experimental work, but it's perfect for your sunscreen lotion. Okay, and that is precisely why they appear clear, because they cannot scatter the light. Okay. All right, these are the summaries. So the meeting is ending in 5 minutes. So since these are two classes, we will immediately join back. Okay, and the second class will be slightly shorter because what's the time now? So I have a meeting from 10:30, so it's almost 10. So it's fine. We'll finish up by 10:25. Okay. So once this meeting is this session finishes, you please join immediately. Now continuing. Now summarizing the magnetic properties, we already discussed about that. The variation or the movement from ferromagnetic property to paramagnetic and super paramagnetic property. Right. So. The magnetic moment of nanoparticles is found to be very less when compared with its bulk size. Okay, so there's a particle size is very small. Okay, and there is a interatomic spacing also goes narrow, means smaller. So the interatomic interactions, that means the interaction between nucleus of one atom and the nucleus of the other atom, plus the interaction between nucleus of one atom and the electrons of the other atoms, and all those things, all these interactions change. Okay, and that's why they're more strong. That's why the moment is less. The magnetic moment is less. For magnetic materials such as iron, cobalt, nickel, ferric oxide, etc., magnetic properties are size dependent. Okay, that means the magnetic moment will change with the change in the size. So for magnetic memory, that means we magnetize something and it remains as a permanent magnet unless we remove it. Okay, that's what is a magnetic memory, right? We use a magnetic field to put in information in the form of different positions of the magnetic moment. All right, and that's how we do the recording, right? Even your flash memory is dead. Previously we used to have these floppy drives and magnetic disks. You don't use them anymore, but all those are magnetic memories, okay, where we magnetize, and uh, this is also size dependent. Okay, the strength of a particle's internal magnetic field can be size dependent. Okay, so magnetic property of a material, be it a permanent magnet or a paramagnet, with size, the magnetic field varies, and normally when the size goes smaller and smaller, the magnetic field impacts are also getting lesser and lesser. Okay. All right. Now summarizing on the physical and chemical properties. So the crystal structure of nanoparticles is the same as the bulk structure with different lattice parameters. That means you know about crystal structure, right? The area, the arrangement of the atoms inside the material. Okay. So there are different ways of looking at it. I mean, basically we say, if we start cutting, a material smaller and smaller and smaller and smaller, okay, then we finally go to a stage, which is if we cut it, it won't be the same anymore, right? So that is what we call as a unit cell. That means a unit cell will have a few atoms, okay, and that one will replicate. That means when you talk about a crystal structure, it can come down to suppose a cube. A cube is a simple, structure. Let me see if I can draw it here. Where is it? Okay, still there. So let me just quickly draw a cube. All right, because of my hand, it is not really, but this you can understand. This is a cube, right? This is a cube. That will be the other side, something like this, no? So a simple, if we have atoms sitting at all these corner points, right? One atom here, these are all the atoms sitting there. So there are 8 atoms sitting at the corner of the cube. This process, this is called as a very simple one. This is the basic, crystal structure is called a simple cubic structure. All right, simple cubic structure. That means if we have to look at the bulk material, it will be simply addition of these, more and more and more, So you simply add this one. So you have one cube. Okay, you can add another cube this side.